Well, people roll in later. We have class today, but next week is, we could have a class on Tuesday, but I've already said no. Thursday class is Will Pettit, then of the Geothermal Resources Council, now of Baker Hughes, talking about how the transition that makes sense for geothermal energy to be more productive is to borrow the technology that made shale gas profitable, horizontal drilling and cased wells and massive hydraulic fracturing perhaps. And so he'll talk a little bit about that. And so from now on in, we'll talk today about geophysics. Next Tuesday will be about drilling for prospecting, but also with a portion of it, a presentation by a guy called Doug Blankenship, who works for DOE Geothermal at Sandia and is seconded to DC half the week perhaps, or half of his time, who's a drilling expert in geothermal, and he made a presentation for us at a meeting we ran in 2016 in Houston, and I glibly and borrowed that from him. It's with attribution because it has his name on it, but I'm not sure I asked him if I could use it or not. It was on my laptop because I was running the meeting. And so that is on Tuesday. Talk about drilling, both for exploration but also for completing wells to be able to make circulation in these reservoirs or to stimulate them in the first place. And then Will Pettit will talk on the Thursday, or you can do it whenever you want. Then after spring break, I think of the material we have left to cover, a lot of it is in cameos of people during COVID that I got to come online and talk to the students, maybe 6 or 8. You've seen one of them already by Jason Pogachnik, who did work for GNS in New Zealand in geothermal, but now works in Belgium for a company, the government research lab, making doublet geothermal wells in low temperature geothermals. So you must have seen that already, I think. You'll have been directed to that. And then after the spring break, maybe we have one on converting hot water and steam into electricity through turbines, kind of the surface plant part of hydrothermal, but the other portions of discussing hydrothermal, EGS, energy storage, and direct use are all taken care of other people other than I in these cameos. So I think it'll be interesting for you to see what their perspectives on that. So after spring break, I think we may have only 2 classes. One in terms of conversion of hot water and steam in surface plant into electricity, and the other one in terms of ground source heat pumps, which might be two lectures. I can't remember now. So all by way of saying that the in-class stuff will start to transition then. So no, next week is not in class for either period. I thought about actually bringing you in so I could do a more recent version of the drilling one, but I won't. No, both out online. So I think the week after spring break there may be 3 online substantive things to look at, just 1 in class and then 2 online instead of just 1 online. So anyway, I don't think this class is too onerous, is it? How are the online videos going? You're not taking the ones for class, but you're taking the ones that have been created by your previous peers. Are they informative or are they a wash?
There's a mix.
Yeah, but that's fine. I understand what you're saying. I can read between the lines. But anyway, the one good thing it does is it allows you to get a grade. I don't know whether you want to take exams or not, but you don't have an exam. And it allows me to kind of in a legitimate way give grades, which I think will be stacked quite high. They should be if you just do the stuff. And you can get whatever information from this class you hope to get. So that's where we are, I think. So we will carry on today talking about resource exploration characterization. We talked last time about needing to know the geological habit where these sites would exist. For hydrothermal deposits, ring of fire, sometimes inside continents, in rift valleys, for instance, sometimes on constructive plate boundaries, spreading ridges like Iceland, and also hotspot locations like Hawaii, Canary Islands, and Cape Verde Islands. And we had a little tour around the world based on that. I see Rhea's not here today. I did invite her not to come because the material we'll talk about today is she's seen in a different class. But so we'll talk about how, if you find yourself in one of these likely geological habits where hydrothermal, where hot fluids exist, maybe shallow within the crust, what you can do to figure out where the best locations might be to look for the sweet spots, so to speak. And I suppose also it comes down to being able to say globally, if you want to be able to use EGS under New York City, close to consumption, how do you figure out whether one place is better than another? And so that's perhaps the dream and the promise of EGS. But of course, things like induced seismicity might preclude doing that. So that's our plan today. We talked in terms of this behavior using this figure, which I think is useful for us to think about. And that is, in setting up any kind of project, at the beginning, you have a huge amount of risk, which you'd like to minimize by knowing something about it. You know something about it by doing a variety of things that we talked about last time, and that is figuring out what the site is, being able to do some kind of site review. Once you think it has some promise, then you might do some drilling. You might then set up a production drilling program to be able to pull fluids out of it. And then if that's successful from the flow test and it looks sustainable, perhaps you might put surface plant on there. And it's this balance between having a huge amount of risk at the beginning, which you can slowly get rid of. A big part of it is by physically drilling into it rather than just looking at it from the outside. And as you do that, it's a progressively larger and larger amount of investment to do that. And so right at the beginning of this, before exploratory drilling, which we'll really talk about next week, there's something that comes in between surface reconnaissance and exploration drilling, which would be geophysics. And so we'll talk about that today. The problem with the geophysics for geothermal reservoirs is, in some cases, that if you're using geophysics to understand the subsurface, you're looking at geophysical properties. And so those geophysical properties would be changes in electrical resistivity. It would be lighter or denser than normal rocks by looking at gravity. It would be electrical conductivity of the subsurface rocks as being indicative of maybe fluids charged with chemicals, which would have high conductivities, electrical conductivities. And so there has to be some signature that you're looking for. The problem is that in many sites, such as EGS sites, they're crystalline rocks. This is salts that we talked about last time. Maybe there's not very much of a signature here. It's a sedimentary aquifer, so it might have more signatures of stratigraphy and beds which might be cap rocks, which keep hot fluids in, and reservoir rocks, which might be below them. So in a sedimentary environment, you might have a lot of information about it. But in places like the geysers, where you specifically have a cap rock underlain by a reservoir and underlain by a superheated reservoir, that might have geological structure with different properties of these stratigraphic regions that you can pick out with geophysics. But in places where you have granitic rocks, maybe quite uniform, and the only fluid flow in those granitic rocks is in fractures which are present everywhere, then there might not be much to be able to see in terms of geothermal signatures. And so geothermal methods might be useful in some cases and less useful in others. So maybe I'll come back to that. So what we'll talk about today, is just to remind ourselves why we were interested in this. And that is, we want to make sure we have hot fluids, and we'd like big flow rates without making them by hydraulic fracturing. We need to do this in EGS systems, which have huge investment. $10 million well to get down maybe to 4,000 meters, 3,000 meters. Less so for shallow ground-sourced heat pumps. But we want to be able to understand whether we're going to get both those temperatures relatively high up in the crust, so we don't have to drill so far, and whether we have fluids that are flowing in the subsurface. And it's very difficult to get either of these directly from geophysical methods. Bless you. And so the methods we'll talk about using are ones that look at ferrous minerals in the subsurface, not very used for us. Looking at electrical conductivities or resistivities in the subsurface, either by using alternating current, direct current, or electromagnetic signals as indicative of that. Using active seismic methods, measuring gravity locally to be able to say something about low density rocks or high density rocks, and doing that all from the surface. And some methods which, if you have a well bore, you can use well bore geophysics to be able to enhance what you have. So the basic idea is that you start off generically on the surface, looking at it, not seeing very much, and you want to know what's going on down here. And so you'd like to do this at low cost. For shallow investigations, you can dig a trench for direct investigation. But for the depths that we're talking about, the only way to get down is a drill hole. So before that, you can use geophysics to be able to look at what might be present. And so the whole idea is that, one, you'd like to know what's present in the subsurface before you do anything else, just to be able to have a low-cost method of being able to see what's going on. Secondly, if and when you do drill, the reality is that the core that you get out of it might be the size of your fist along a linear trajectory and not very representative of a very big block of rock. And so if you use geophysics to look at some parameter as to how it changes as you go across the site, you can use that to ground truth against what's in a borehole. So if you know what's in a borehole has some specific acoustic velocity or resistivity or density. Density is the same signal we'll use today for resistivity. If you can measure that in the borehole and you find that in your geophysical characterization to be present at the same depth, then you can extrapolate beds across in the subsurface that might allow you to say a lot more as to what's going on over the full area of the reservoir than you can just from taking a single drill hole. And so you might be interested in, as in salts, pulling out the locations of faults, which might be locations where flow of fluids would travel along these perhaps more permeable regions than are present otherwise. So that's the essence of what we're trying to do. The other thing that would inform what's going on, I'm going to bring up the course notes for what we've done. It might take a little while to load because they're big. I can't pick up the hot link from my notability notes, so I'll go back to here. This will remind you of how much joy or pain you've been through so far. I'm not sure which it'll be. So I wanted to go right here. Opens in a PDF, but it doesn't open in Notability. I guess I could have downloaded it before and put it on my desktop. And so one good implementation of this is reports for this particular project. I'll open the report, but I'll go back here. I guess I can go back here. So, FORGE is a US DOE demonstration project in the geothermal office. It initiated, does it have years on it? It probably initiated in the early 2010s, teens, I guess. So you go. The idea was to take $150 million that had been squirreled away in the geothermal program that didn't have to be cleared out by the end of the year, had been accumulated over some time, and have a very large demonstration project to make a EGS reservoir specifically to understand the mechanisms by which you could develop these reservoirs successfully. Never to be able to produce electricity from it, but just to use it as a case study. And so what it started off with was a call that was open to everybody. A number of proposals submitted, maybe about 6. Of those 6, they were given a small amount of money to do some work to develop their proposals. I think all of them got money to drill a hole to be able to characterize things. Then out of those 6, there's a down select to get to 2. So yeah, I think perhaps it was 5. So these are the 5 proposals. There's a down select to get to 2. They got some more money to do some characterization. And then there was a final choice of what was Utah Forge in Milford in the state of Utah, run by the University of Utah and the Energy Resources Institute there. And then that location was developed by investing maybe $70 million to develop the site, drilling. That all disappears very quickly. And then maybe $70 million to do the science that goes with that. And so this is documenting the 5 sites that went ahead. And one of those, this, is it not completed? Is it not going to do this? Let me go back and open it again. I don't know what I did. That would be a shame if it doesn't open. I think that's what it was. Don't know why. No idea why it won't open. I don't know if I've downloaded a version of it yesterday. Doesn't look like it. So, well, that puts a crimp in my plan, unfortunately. I don't know why. So I guess hitting that again probably isn't going to do me any good. Just doesn't want to come open. I guess it may be downloading multiple copies at the same time, which might not be a great deal. Great. Okay, plan B. Always, sorry to keep you waiting, but always be a problem solver. Let's try this then. So this report, so there were 5 sites that were chosen. 2 of them were on military reservations. And one Coastal Geothermal Plant, which is an active geothermal plant on the China Lake Weapons Reservation, east of LA, and the other one is Fallon Air Force Base in Nevada. But this was report for the first one of these, COSO geothermal. The requirement for the Forge project was, since it wanted to look at EGS sites particularly, they didn't specifically want it to be a hydrothermal site. So one requirement was that the permeability be less than some number, maybe less than 10 to the minus 14 meters squared, and be away from any active fluids, but also at the same time maybe be greater than 200 degrees centigrade. So those are two primary requirements. So this idea went ahead. So these sites did prospecting, and the prospecting would include things like geological surveys, understanding of the geology in geological USGS reports at the location, to understand the geological habit, such as this cartoon is showing here at this particular location, and other maps which would map the geology of the region, which could be done photogrammetrically from the air, but also in terms of any drilling which was available. Of course, COSO, which exists here, has lots of wells in place, and so there were lots of data available for this. But this is a matrix of the kinds of things that you might want to determine in addition to prospecting. So for this research project, which it really was rather than a commercial site, it talked about methods to be able to image for the stress regime at depth. Stresses on fractures that get relieved as you pump cold fluids define the changes in permeability you get. And so if you want to get stress regimes, you can get it from things like wellbore imaging for breakouts, which are failures in the side bores of the well bores, which give you orientations of the fractures. Understanding for earthquakes, focal mechanisms. The form of slip that occurred can be defined by looking at the first arrivals on in situ seismometers, and use that to determine what the slip directions on faults are to be able to constrain stresses. Trying to get temperatures. Pretty much the only way you can get temperature would be if you had shallow well bores at different depths and you had a geothermal gradient defined by those. You could extrapolate that at depth to understand exactly how the extrapolated temperature was. Otherwise, you have to actually drill a well. And so at this particular place, they had pre-existing wells to define that. To be able to identify permeability, you need to have access also to be able to run a pump test, to be able to look at the rates at which you can pump fluids in, compare that with the volumes that go in at those pressures, and use Darcy's law to be able to figure out what permeabilities are. To make sure, in this case, a requirement for this project to be chosen would be that no pre-existing hydrothermal system exists. So the permeability had to be low, and you had to be either on the flanks of a hydrothermal system, which is what Forge is. There's a hydrothermal system very close by, which is, I can't remember the name of the plant right now, which is producing hydrothermal energy converted into electricity, but this was on a granitic flank of that, which had almost no circulation in it all, but was guaranteed to have temperatures just because we knew about it from the site next door. So these would be the kinds of things that you'd like to determine at a site. Some of them you can only get by drilling, some of them you might be able to infer by the geophysics, and some of them you might be able to infer also from the geology and tectonics which exist at that location. So that's kind of the first things you want to do are the ones that cost the least and reveal the largest change in your knowledge. From knowing nothing about it to knowing something is an infinite change, and everything after that would be incremental. So knowing something about the geophysics would help you reduce the risk. Knowing something by direct drilling and knowing what's down there, temperatures and confirming a reservoir would help you. Running pump tests with those boreholes would confirm something else, and so forth. So the idea is that you can successively reduce risk, and we'll talk about doing it by trying, in some case, to use these geophysical methods, which merely measure a geophysical property, the magnetic form composition of the rocks, or magnetic properties of the rocks, the conductive or resistive properties of the rocks, the seismic velocity of the rocks, or their density as indicated by measuring the local value of the acceleration due to gravity, g, and inferring that that means low or high density rocks depending on how it takes it. And again, I'll stress that some of these are a bit difficult to use because there's not much structure, especially in EGS reservoirs, that you could look for. You can't look for a cap rock because it's not there. They're relatively homogeneous materials and are difficult to pick up by the proxy measurements of magnetism, conductivity, acoustic velocity, or density, which are proxies for some characteristic of the reservoir, which would say that it's a good geothermal bed. So some of these we'll go through quickly, just to give you an appreciation of what can be done. Geomagnetic methods merely look for the presence of iron. So it's used mainly in things like looking for, in contaminant hydrology, looking for buried drums in the subsurface. It works on the principle that the Earth has a geomagnetic field with flow lines of that field going through the North Pole, magnetic North Pole and magnetic South Pole. These are fields of potential, of magnetic influence that solar rain from the sun interact with to give you the aurora borealis or australis in the south. And these lines of flux at any particular latitude would impinge on the Earth. And I thought I did have a picture of the latitudes here. I didn't see it. So they would have a specific angle as they pass through the Earth. And if you have something which is ferrous, they will preferentially go through that and they'll change the separation between these flow lines. So if you run a traverse across these flow lines and measure the magnetic field across these, you can determine where you might have a concentration of iron below the surface. So the idea would be to make a traverse. If you make the traverse with very deeply buried deposits, you'll get a signal which won't be very high amplitude and will be quite diffuse because it won't pick out individual components. But if you do a traverse which is shallower, if the objects are actually higher up in the stratigraphy, it will actually pick out individual features, and actually the magnitude of this, the measured magnitude of the magnetic field will be much larger as you're closer to the individual deposits. So in terms of these materials, if you look up if I look at images, so they come in a variety of formats. It's almost like using GPS, like a Trimble. Guess I couldn't do that before. It's like moving across from location to location, measuring the magnitude of the magnetic field at those individual locations. Sometimes you see them as horizontal bars that you walk across a field with, and they're useful for being able to, they're used for prospecting ores in many respects, because even though it will only pick up magnetic minerals, iron in other words, it can also be used to be able to, those are often associated with other mineral ores such as gold, etc. So you walk across a field, you do the prospecting, and you draw a plan. From that, you can actually quantitatively evaluate them by looking at the form of this individual peak and valley. And because in where we are at this latitude, or this is perhaps higher latitudes, the individual lines of magnetic flux come in at a particular angle. This is skewed. If they came in exactly vertically, then this would be symmetric with a trough on either side and a peak in the middle. You can use this not only to identify the location, you can define the depth as a function of the coordinates on this graph. From peak to trough, and the length between those on the surface defines the likely depth as you are. And that happens because we're able to define the angle of entry of the magnetic flux lines at a particular latitude on the surface of the Earth. And so these are instruments that merely have a coil that measures the spin of the hydrogen atoms within water, which is inside it, and is able to give you out a reading in terms of the magnetic magnitude of that location in terms of nanoteslas, teslas to the -9. So first form is using magnetic methods. Electrical methods come in a variety of forms. We mentioned before AC, DC, and electromagnetic methods. But in addition to those different formats, measuring them, you can imagine running them in two different modes. And they are in terms of profiling and sounding. So the idea of sounding is that you take an array and you set up that array at a particular location, and then you pull it down and you set it up progressively at a whole bunch of different locations. These arrays individually measure the electrical resistivity, or 1 over resistivity as conductivity, at a single depth, because they're electrodes that are spaced on a particular baseline. So it always measures at a certain depth, but it measures the resistivity of that depth along a traverse. And so if you plot the magnitude of the resistivity along that traverse, you can use it to identify areas of low resistivity and high resistivity. And if you think that those correlate with some geophysical signature that would represent a reservoir, then you can use those to be able to interpret where you might find that. The other way to use it is not as sounding, but as profiling. So now the idea is that you take the profile and you measure it with electrodes maybe along that profile, and then you expand the section so now it's longer. And so as you get a longer section, you progressively probe deeper and deeper into the subsurface. So by widening the length of your traverse array of electrodes, you can progressively look deeper and deeper. So now the measurements that you get of resistivity at these different depths, it's given the symbol of gamma, you can plot that as depth versus this resistivity. So this is really saying that as you go deeper in the crust, the reduced data that you get from making these measurements would give you some profile in the subsurface of exactly what your resistivity looks like as a function of depth. And you can do it in that way. So profiling versus things. So actually I did it the wrong way around. This was talking about profiling and this one was dealing with sounding, but you get the idea. So the idea is that you can use Ohm's law, where voltage equals resistivity times amperage. So this is the resistance. Usually you define this as the resistance in terms of ohms for a resistor in a circuit, but so that would be a piece of, this would be a resistor here, and you define the resistance as omega in terms of ohms. But the reality is that in the subsurface we have a resistivity. And that resistivity is in terms of ohm meters. And the idea is that instead of being a single component that has a resistance, the resistivity reflects the fact that it has a resistance per unit length along its length, and it also has a cross-sectional area. So we can apply that just like we can Darcy's law. We have in Darcy's law Q equals K delta H. This, whoops, sorry. This is equivalent to voltage. So I guess it's this, right? This is equivalent to voltage, and this is equivalent to flux. So this happens to be electrical flux, this happens to be a fluid flux, but Ohm's law and Darcy's law and Fourier's law and Fick's law are all similar in that they relate a flux to a gradient. And that, in this case, is defined for electrical flow. So all you do is you prospect by measuring the resistivity of the subsurface. It's set up in a way that you have electrodes at which you have a car battery, positive and negative, stuck in the ground, maybe a piece of rebar, not very sophisticated, and you have another piece of rebar interior to that, and you measure the change in voltage across that rebar, which is produced by putting in a current into the ground at these two individual locations. And so in profiling, you take this arrangement of the arrays and you physically keep it the same separation and just move it down gradient, all parallel to these things, and that gives you a measurement of the change in the resistivity along the direction that you're migrating them. So you're doing this, so it'll measure the resistivity at a particular depth, equivalent depth along the traverse. You can imagine that as you get these wider and wider apart, then this self-similar picture of flow lines, flow of electrons on this trajectory, equipotentials being these perpendicular lines, just like flow charts. As you expand it laterally, you progressively penetrate, sample deeper and deeper in the crust. So as you expand it to do profiling, as you measure at each of these growing separations, that will represent a resistivity that's present progressively deeper and deeper in the crust. And if there's some signal that you can see at depth that relates to a change in resistivity that relates to something in a geothermal system, then that allows you to be able to define that you might have a reservoir there or not. Of course, there are different, probably more information than we need to apply, but the Schlumberger brothers got their start as in looking at electrical resistance characterization in the subsurface. A so-called Schlumberger array says the proportions of the spacing between the injection electrodes and the voltage measuring electrodes. You expand this out progressively if you're doing depth profiling, and you translate it along the surface if you're doing a profile on the ground. A so-called Venner array and a dipole-dipole array are different layouts of the electrodes, which mean that you use different methods to be able to reduce the data to either get, I guess for profiling, you'd get a resistivity profile along the distance that you move it along the ground, or in depth profiling, you get a resistivity profile with depth. And so this would be this. So this would be the resistivity at this particular depth, or this would be the resistivity at a particular depth as you move laterally along a section. And you can calculate an apparent resistivity by measuring the injected amperage, the voltage drop, a factor that allows for this geometry, and come up with a specific resistivity which represents that location in the crust. And so if that has a characteristic which would be indicative of a geothermal reservoir, then you get that. I guess this was a useful thing. So keeping it at the same spacing, like four staples, and moving it from location to location, you get a measurement of resistivity at the same average depth as you go across section, and that would represent the fact that you have a high resistivity at this particular crossing. Conversely here, you measure the resistivity at progressive depths, as in here, and you do it just by expanding the array. And typical materials have different characteristic specific resistivities. And so if you have a contrast in the resistivity of those materials, you can actually pick that up. The one place where that is used, I guess I can see if this actually works for me this time. Oh, that's a video, is the EGS. I think this is it. So this isn't a geothermal, well, could be a geothermal site. The other thing I didn't mention was, in the years in which Forge was going through this very specific down select, having 5 teams, then 2 teams do some investigation, something like a 5-year period, the money that was sitting in the bank had to be spent in some form, and it was used to run what was called the EGS Collab, collaboration experiment with a bunch of national labs and a number of universities invited to do this. And what it was to investigate the methods of being able to create permeability within a reservoir that would never be a geothermal reservoir because it's too shallow, but you could get close in to understand the mechanisms by which you could increase permeability by increasing pressures below the hydraulic fracturing pressure, where you induce shear on fractures, and then in other experiments actually hydrofracture the reservoir to see what the difference would be. And it was conducted in the Sanford Underground Research Lab, which is the old Homestake gold mine in the Black Hills of South Dakota, in the southwest corner of South Dakota. The gold mine is not operational anymore. It's now a big physics underground research lab. The main portion of it is at 1,500 meters, the 4,750 feet level below the surface. And in concert with this big construction to create a neutrino detector at 1,500 meters, the tunnels that access that were used to actually run this EGS Collab experiment. And so what it was a single tunnel at that depth, which had an injection borehole, a recovery borehole, and a monitoring borehole present in it. And so within this injection borehole, you could pack off a portion of the borehole which you'd inject fluids, and you try and use that to stimulate this region to be able to link up with the recovery borehole. You'd flow fluids through it, and so that if you had a pressure drop between these two, and you could measure the flow rates that you inject and then recover, you can use Darcy's law to calculate what the permeability is, and so you can try different stimulation methods to better do this. And so concurrently with this, these central boreholes were to monitor what's going on, and these other fans of boreholes, so the injection and recovery boreholes went like this, the fans of boreholes went above and below it, and these were instrumented with continuous active seismic. So you make a small seismic pulse, which you then measure along this other borehole, and that of course traverses the zone pardon me, in which you're flowing fluids through. So you can use that to look at micro-earthquakes that you generate and try and understand what those micro-earthquakes mean in terms of making permeability. And you can also, in these boreholes, run electrical resistance measurements. And so these electrical measurements would do, you could imagine that if you had, in plan view, if this was your adit, and these were your injection recovery holes, which you are flowing fluid into the formation, then these monitoring boreholes were above and below. And so you can imagine that if you have both seismometers arranged all along here and receivers based all along here, then you can basically shoot across here with a pulse, and you can measure the travel time, you can get the acoustic velocity of this zone, and you can use that to say something about what's changing as you do this. So just like in a hospital CAT scan, you can shoot from this point to this point, and you can shoot from here to, you will shoot from here to here, etc. And you can do the opposite in the opposite direction. So along these ray paths, you have individual acoustic seismic velocities, and so you can reduce this data to make a contour map, just like a CT scan of your brain. It's measuring CT number as you get across your brain or any part of your body. And so you can use in situ tomography to measure changes in the reservoir. And so you can do it with seismic velocities, but you can do it also by injecting a current, recovering a current in these locations, and using that to calculate how the electrical resistivity changes in this region. And so one big constraint on electrical resistivity is whether the material is wet or dry. And I can't look at this. You can see all kinds of interesting parameters on this. I don't see, do they have paper? Yeah. There's certainly a big contrast between wet rocks and dry rocks, and there's certainly a contrast in wet rocks with distilled water in, or wet rocks with brine. And so you can use that to see where fluids might be traveling, and you can see that to identify where you might be making permeability, and to understand the processes by which you're making it, by trying out different stimulation methods to see how effective they might be. So using DC methods to measure an injection of current into here across to a recovery location on the other side, use that to measure the drop in voltage across that, and from Ohm's law, use that to calculate how resistivity, specific resistivity, might change in this particular location. And so there are different ways. Other things to use this for, it's been used for, to use electrical resistance tomography at the surface. So the idea is you have a contaminated site. This is where they used to land the space shuttle in California. Contaminated by solvents, it's got into the ground surface. You want to remediate it, so you drill some holes and you pump steam through those holes. These solvents have low boiling points, so you can vaporize them. And as you vaporize them, you change the electrical resistivity between monitoring locations that would be just like these fans of boreholes and would be able to pull out the magnitude of this. So these should be in color, but they're not. They give you the changing location of resistivity. You use that as a proxy as changing saturation of these non-aqueous phase liquids that you want to get out of the system. And so when they disappear on the electrical resistance tomography plot, you know that you might have cleared the section. So that's one way of using electrical resistivity tomography. So that's for a very different project. That's looking at how to understand processes in the subsurface where you're doing something to a reservoir or a potential reservoir or a proxy for a reservoir, and seeing how different stimulation methods would allow you to make a reservoir that has high fluid throughput and also makes surface area. All the two requirements that you want for an EGS reservoir. You don't care about temperatures in this case because it's never going to be used as a geothermal reservoir. The in situ temperature probably is 30 degrees centigrade only. And so magnetotellurics are the same idea, where you go onto a site. This is actually is the COSO site for the potential Forge project, which is in Southern California. You set up instruments on a grid of locations. This is actually the boundary of the potential field site. So this is probably a couple of kilometers by a kilometer in size. So that gives you the spread, how big the spread is of these individual measurement locations are. And what this does is it uses the natural currents present within the Earth's crust to be able to create a map of electrical conductivity within the reservoir at reservoir depth. And so you run this by monitoring it by a field campaign at one, maybe in 2015. You come back in 5 years in 2020, deploy them again, and you use that to be able to draw a map of electrical conductivity in the subsurface. So this is such a map, and this shows that in this particular site, I mentioned that one of the requirements was that it couldn't be a hydrothermal system because it wanted to test EGS as a technology, so no large fluxes of water, but did need to be hot. So it was on the flanks of an existing hydrothermal reservoir, and so this represents that reservoir where water with large concentrations of dissolved components, just like when we talked about geochemistry, we talked about 60,000 ppm of salts being present in some reservoirs, and seawater is 35,000, so very saline waters, very high conductivities or low resistivities, and as a result this picks up that. So if you're prospecting for a hydrothermal reservoir, this would pick it up. But here, interestingly enough, it was used to delineate the boundaries of this hydrothermal reservoir, ensure that the prospective forge site did not have hydrothermal circulation that would have disqualified it, and that therefore it could be used as a pristine site to develop permeability. And so magnetotellurics is one way at large scale to be able to do the same things that we just talked about for a very specific application to measure electrical resistance tomography in the subsurface. So this was at 1,500 meters depth. And so the other thing here, I guess, is that if you're using seismics, you'd like to be very close to the action. So the scale of this might be of the order of 50 meters. But it's 1,500 meters below surface. So if you wanted to measure the acoustic emissions and where you're developing failure in the reservoir from the surface, then here, the seismometers that would be deployed on the surface would be 1,500 meters away. If you do it with access by drilling from the adit, you're only 50 meters away, and you have much better control on locating those events in space, and that is what allows you to say something about this reservoir that you're trying to develop. So DC type electrical methods, one by putting current into the ground yourselves, actively I guess, and the other one in magnetotellurics in using the natural magnetic field of the Earth to generate current in the subsurface, which you can then invert to be able to come with a map of resistivity and use the proxy measurement of electrical resistivity to represent the high concentrations of conductive fluids, salts, in the subsurface as indicative of fluid circulation. You can use other methods that do this by injecting DC energy into the subsurface, measuring it on another location. So these would be two electrodes that would inject current into the subsurface, and these would measure the voltage that develops. But what would be done was you inject current into the surface, then turn it off, then do it the other way around, from one electrode to the other, etc. And you'd measure the voltage response building as you start this up, coming to steady state, and then dropping as you turn it off. And so from that lag time and that response to the charge up and the charge down, you can say something about, again, the electrical conductivities or resistivities at depth. And if you think what you're looking for is amenable to having a signature that changes, has a signal on the electrical conductivity, then you can use that as a prospecting way, just as you would do here. High conductivities represent an active hydrothermal reservoir. You can do it by coils with electromagnetics. So instead of looking at the DC signal, by providing an AC signal, you can develop something that puts electromagnetic radiation, radar, low frequency radiation to the ground. You put a coil somewhere to be able to measure the changes, perhaps in an ore body, which is a good conductor of that electromagnetic radiation, and you use that to be able to, again, figure out exactly what's going on the subsurface. And so this is low frequency radio waves is a method by which on land you used to be able to communicate with submarines. So low frequencies, if you manage, think about low frequency acoustic waves put into the ground, they attenuate very quickly close to the source because they, through inertia, they try and move things backwards and forwards very quickly and therefore dissipate at energy very, very fast and very close to the source. Low frequency seismic energy and low frequency electromagnetic energy tend to change only very slowly, so you get a long time to put it into the ground and a long time to pull it back out, so they travel much more distally. So the lower the frequency, the deeper the penetration that you can look at. And so all by way of saying that the one way to communicate with subsurface, not coming up to land, was to be able to have low frequency electromagnetic waves that would also penetrate the ocean and go down and be picked up by the transmitters at depth as submarines did their thing. The not so useful for geothermal prospecting, but used in environmental prospecting, is using radar. So radar is physically the same radar that you use, that you hope your plane is using when you're landing, to be able to send out an electromagnetic pulse from a transmitter, have it bounce off something that has a contrasting dielectric constant and sends it back to a receiver. The fact that there's a contrasting dielectric behavior of these two materials means that there's a reflection off this boundary, and if you know the travel time for it to hit this reflector and come back, or the two-way travel time, and if you know the velocity of the electromagnetic radiation, which is pretty close to the speed of light, then you can make a calculation from velocity is equal to length over time. You can turn that around to time. Sorry, you don't want that. You want length is equal to velocity times time. So if you know the two-way travel time, you know the velocity is close to the speed of light, then if you measure those two components, you can say exactly what this depth is. Problem is that even if you use the lowest frequency electromagnetic radiation, the penetration of this is probably 100 meters. So not so useful for geothermal, but works on the similar principle that you're using contrasts in the dielectric constant that define a reflector, and the speed to be able to define the arrival time to define the speed. So you get a trace that looks like this. It looks just like seismic. This is actually a trace across the frozen Mackenzie River just below the Arctic Circle. This is the ground surface representing time of 0. These represents the two-way travel time. So this would be the time to go down and then up again to the surface. And so this is just a trace. So this over here would represent a short travel time, a long travel time. And so this represents some indication of a dipping interface that has a contrasting characteristic between one material and the other. And if that's relevant for you searching for geothermal energy, then that's useful. It's probably isn't very useful for geothermal because 100 meters isn't really deep enough. So this happened to be, these signals were a reflection from ice into water. So this was the base of the frozen river ice on top of the river. This was water in here. So this is water, this is ice, and this is the riverbed. This is actually the site I might have shown you in Northwest Territories with these river islands. Used the drilling pads to be able to drill into a anticline. And of course, to be able to justify exactly what these boundaries are, you ground truth it against a borehole. The borehole identifies that the thickness of the ice is such and such. I guess this must be another signal in here, interface, that there's water to a certain depth, and that there's sediment to a certain depth, I guess. And I think this is bedrock underneath that. And so you can use that. So this idea of having a geophysical method to represent the distribution of some parameter that's a proxy for the characteristics of the reservoir over a large area, but to ground truth it with the few boreholes you have that give you very precise data, but not to a very large geographic range. And so it's a standard way that you can use to do this. And of course, this kind of behavior that you're looking at here is no different from using seismic methods, which would be able to penetrate to 5 kilometers, but only are useful if it can pick up some kind of interface which means something. And so seismic methods come in 2 flavors. We're mainly interested in reflected prospecting as opposed to seismic refraction. The idea for each of them are that seismic refraction has an explosion on the surface, a whole bunch of geophones on the surface which pick up the timing of the first arrivals. So time, it measures the impulse of first arrival of the impulse that dies out. So it gives an arrival time, T arrival. And so with those arrivals from this surface, you can identify what the characteristic seismic velocities and thicknesses are of these reservoirs to this feature of interest in the subsurface. So the 2 modes of behavior are refraction and reflection and refraction. Refraction is that the wave finds this interface, and once it gets this interface, it gets refracted along it and travels to some distance and then comes up to meet the geophone which is present on the surface. Typically, the seismic velocity of zone 2 is larger than that of V1. So as you get deeper, they get progressively faster. So this ray path goes across a slow layer, but then gets into the superhighway and can travel a long distance laterally and then zip up again through the slow layer to reach the location on the surface before the ray path that stays all the time in the slow layer. So this is a shorter distance than this would be, but this is always in the low velocity layer. This actually has some time within the high velocity layer. So the first arrival here will be this refracted wave. Conversely, it used to be that reflected signals were used for petroleum engineering because the distance to the reservoir was maybe 5 kilometers versus 50 meters. And so for the refracted wave, the measurements in terms of the arrival times weren't at sufficiently good resolution to be able to pick up this refracted wave. And so it used to be that refraction was used for shallow geophysics and reflection for deep, but now refraction with the instrumentation can actually cover refracted behaviors at all. For geothermal, we'd almost always use reflected waves. This is the setup, and this is the idea, I guess. You'd put a whole bunch of geophones on the surface. You'd have a shot point where you set off, either hit a plate with a sledgehammer, or set off a small explosion, or set off a big explosion. This would provide a wave that would go into the subsurface, and that wave would get somewhere after 10 milliseconds, 20 milliseconds, 30 milliseconds, etc. And these geophones would pick up these individual arrival times as it arrives at this geophone. And if you plot these arrival times, switch it vertically, you'd end up with something that looks like this. So this is the surface. This is arrival time T0. This would arrive after 10 seconds, 20 seconds, 30 seconds, 40 seconds. These would be the two-way travel times. So these little blips are indicative of the underlying geometry of the interfaces. And since you know the arrival times, and if you know the velocities of these different components, V1, V2, etc., then you can, from knowing the location of the geophones and the time it takes for the first arrival time to get there, you can make a plot like this. So this would give a series of geophone measurements. They might have a kink in them, and this kink would represent the fact that up to this location here, it's faster for it to go down to this high velocity layer, go along the interface, and then come up. It will arrive then before the reflected wave that does this, which would be this speed along here. So this kink in the distance arrival time identifies when it changes over from being a refracted arrival versus a reflected arrival. And so from this coordinate here on this map, you're able to pick out this gradient would give you the velocity. It's just the distance traveled in a time. Velocity equals length over time. So this gradient gives you the velocity of this upper layer. And if you know the velocity and the arrival time at this, representing the two-way travel time, it also gives you this distance. So together, it gives you the location of these boundaries at depth. So the only important thing is that you actually have a boundary that has a contrasting seismic velocity. So at geysers, a cap rock, which would be clays, would probably have a smaller seismic velocity than the reservoir underneath it and the superhot reservoir under that. And so you could use that to prospect for those behaviors. So seismic behaviors, this is seismic reflection, I guess. This is exactly the same idea as before. Sometimes in these things you don't have an explosion in geophones. You always have geophones, but you might have a vibro size. So all that does is it puts energy into the crust, and you look at the arrivals of those individual pulses from basically a bulldozer, actually a purpose-made truck with off-road, high clearance, that's able to have a big heavy plate that goes down on the ground, and then some oscillator with a mass in the body of this, which makes the plate vibrate at some frequency and put out seismic energy, picked up on the surface. The same idea as before is you look at the arrivals at these geophones, and these give you an idea of the form of the interface that you're seeing as you measure in the geophones along this trajectory. So in oil field characterization, this might be 10 kilometers. To be able to look down 10 kilometers, I suppose you can look down about as far as the width of your array is. So if you want to be able to look down 20 kilometers, you have to spread that out even further. But you can calibrate this interface for both the velocities of the material above and below it, and also the absolute depth orientation is. So if you have a signal of a cap rock that you can define, then you can surmise perhaps that you might have a geothermal reservoir underneath that. 118. Getting towards root zone. And finally, not very used in geothermal prospecting is using gravity methods. So gravity methods merely look for the fact that the rock underneath a monitoring location might have a lower density. And that lower density is manifest as a change in the gravitational acceleration, 9.81 meters a second squared. And so where you have lower density rock, Newton's law of gravity defines this gravitational constant as the attraction between a big body, the Earth, and a smaller body as something present on the Earth in terms of these coefficients. So if you imagine going across a place where you have a void where the density of something is much lower than the surrounding material, if you had a spring that would measure by its extension the gravitational constant at this location, because this is a weight which is applying a force, if you can measure this, if you know the weight and you can measure the force in this spring, you can calculate exactly what this is. And so you'd expect that as you go across a hole in the ground which doesn't have much mass in it, the spring would not be as extended as it would be otherwise, and that would be an indication of a reduced coefficient of gravitational acceleration. And so you can calculate this very accurately. So you can run a profile by setting up an instrument going across the surface at these individual locations, plot the value of G as you go across here, and be able to identify the fact that this has a lower density. Problem is that the measurements are tiny changes in G, and lots of things like elevation, the presence of terrain, have much larger signal than this signal for this. So you have to make big corrections to be able to do that. And actually the signal for geothermal reservoirs wouldn't be a signal that you'd see. And finally, these are all methods that can be applied very easily on the surface. They need to have something that you're looking for that has a geophysical signal. Electrical conductivity, density, magnetics, or seismic velocity. If it doesn't have those contrasts, you can't use it per se. The other form of geophysics is wellbore geophysics, and that is if you do, after you perform your geophysical survey, drill a hole, then in that hole you can drop a sonde. And a sonde is merely an instrument on a wire line that measures something like the acoustic velocity between a transmitter and receiver up and down and separated by maybe a couple of meters within the borehole, measures the electrical resistivity in the wall rocks, has an active source to measure the moisture content, active radioactive source to measure the moisture content with depth, has a caliper log which measures the width of the borehole, whether it widens at any particular location as an indicator of a different material, and then combines all of these particular signals, electrical conductance, seismic velocity, a density log, a porosity log, a log that represents the size of the borehole as it widens, and then looks at those signals as you go down the depth of the borehole, and use how one increases or one decreases as a proxy to be able to make a best guess as to what the characteristics at that particular location in the borehole are. Is it a shale with intrinsic radioactivity which is measured? Is it some other formation because of the high resistivity? So gamma would measure the radioactive mineral content. You can measure the density. You can measure the conductivity or the resistivity, and you could use that to be able to say what's present at depth. But more importantly, you can use it as ground truth to be able to calibrate the other geophysical measurements that you might have made. So you have an absolute determination of that geophysical proxy within the wellbore. You know exactly what those rocks are if you either recover core or if you use a borehole televiewer. and you have that measurement of that geophysical proxy to correlate what your geophysical survey is telling you in terms of the different characteristics that we've talked about. And so that's probably about it. So not all of these methods would be useful. We alluded to some that would be. The main ones for us for geophysics would be measurements of electrical resistivity measured either by DC, electrical, or magnetotellurics. Also, seismic would be very common to use, but seismics would only work if there's a structure in the subsurface and a target that you can reflect off, and therefore use that to be able to figure out what's going on. So for the last part of this, we need to do drilling to be able to directly ground truth these things, to recover samples, to measure what the geophysical proxies are in terms of magnitude, and then to use those in the subsurface. And so there's a recording online that will talk about that on Tuesday, and then Will Pettit will talk about using oil field techniques in geothermal applications to be able to recover fluids from the well itself. Okay, so I'll stop.